Hello everyone, I'm Zhang from China. Today I'm very glad here to present our work, Empowering chip-level functional key plug-and-play for next-generation IoT device. The main function of IoT end device is to sense the world and provide data support for different IoT applications, such as smart transportation, modern agriculture, and smart healthcare. In the current architecture, IoT end devices run as independent embedded microcomputers. In functional aspects, its main functions are provided by different functional chips. For instance, we can deploy a temperature sensor chip on the device to sense the ambient temperature, or we can deploy a flash memory chip to write and store the data. However, to control different functional chips, it is required to deploy a microprocessor as a control center. Such an architecture makes the end device become an independent microcomputer, which can control functional chips for different applications by embedded programming and hardware customization, but has two issues in practical usage. First, as functional chips are highly different on their control logic and signal, developers have to make customization on both the software and hardware aspects to couple the microprocessor with the target functional chips and ensure the reliable interaction between them. Even with the help of various programming technology or modular device design, developers still need to complete all development process before updating the program or deploying the modular on the device to ensure system working, which makes it difficult to update chip functions on IoT end device and hard to meet the ever-changing requirements of IoT. Second, although the microprocessor is not the main functional component on the device, it also brings additional power consumption and hardware costs, which may reduce the battery life and increase maintenance cost in long-term usage, thus not conducive to large-scale deployments. To address above issue, we propose a new application architecture called Lega that supports chip-level functional key plug-and-play with simple hardware architecture. The core idea is to couple the control of functional chips from distributed end device to a centralized gateway for unified access and control. In the design, the user does not need to program the microprocessor on the end device, but can directly plug in functional chips for new functions. The gateway can automatically recognize the newly plugged chip and generates the required logic for its control. By this, the end device does not need to deploy a microprocessor anymore, where we can design a simple circuit on it to convert the gateway instructions into required underlying physical signals for chip control, which simplifies the device architecture with lower power consumption and costs, and supports chip-level functionality plug-and-play for various application scenarios. To achieve this design, we need to address three technical challenges in control logic, signal interaction, and communication. First, as different functional chips are highly heterogeneous in their pin function, control logic, signal timing, and data format, so it is non-trivial for a Lega gateway to dynamically generate the required control logic for various functional chips mounted on Lega device. Second, it is challenging for Lega device to provide all the required underlying signals for the control of various onboard chips by a simple circuit, without the help of microprocessor and manual modifications. Finally, decoupling the chip control all back to the gateway could effectively avoid manual modifications on Lega device when plug-and-play functional chips, and allow the device to operate without a microprocessor for lower cost and power consumption. However, this brings additional communication overheads. How can we reduce the communication overhead in the remote chip control? To settle above challenge, we built up the Lega system and integrate the gateway and end devices into a unified computing entirety, which simplifies the end device to a various peripheral of the gateway, supporting plug-and-play of various functional chips with simple architecture, reducing developing cost, hardware cost, and power consumption. First, to achieve unified chip access, we design a novel unified chip description language with meta operations to describe chip specifications uniformly. Through in-depth research, we have found that most functional chips are operated in the state machine, where specific single inputs can trigger the chip jump to the next state, and a series of state transitions forms up the required chip functions, such as data rigging. That means we control the chip jumps to a state that we can read out the data. Therefore, we call the basic operation for state jump as a meta operation. Through extensive research and analysis, we have discovered that the meta operations can be summarized into 4 types: data write, data read, control bit write, such as pull up the select line, and the state bit read, such as check the interrupt. In addition, connection configuration and chip output firing are also required in the chip control. So we designed 6 keywords in the description language to query the configuration and operation of functional chips respectively. Based on the description language, we can easily provide the direct logic expression for different functional chips. This page gives the description of an AGXL acceleration sensor chip. When the chip is plugged into a local device, the gateway will automatically retrieve the corresponding description file from the library and encode the file into binary commands for chip control. Second, to settle the challenge on signal interaction, we have designed a universal signal conversion circuit serve as a middleware that connects the gateway and the various deployed chips on local device. The circuit is passively driven by the description language, where the pin keywords control the dynamic connection configuration for pins on the target chip. DW and DR keywords control the bus kernel for data write in and read out. Besides, the CW and SR keywords control the latch and trigger for control bit write in and the state bit read out respectively. By this, we can achieve unified access for various types of functional chips without the help of microprocessor. Finally, to reduce communication overheads in remote chip control, we have designed a lower 3-layer instruction orchestration model and a layered buffer on the gateway and the local device side respectively. The orchestration model consists of 3 layers: chip, function, and meta operation. The lowest level instructions contain a meta operation and its timing. Then, multiple instructions are combined in series to form a control sequence for a specific chip function. Finally, a chip can contain 1 or more functions carried by the control sequence. Based on this design, the complete control command for a chip only needs to be issued once after it is plugged into a local device. The layered buffer on the device will divide and store the instruction with independent chip function blocks. By this, the gateway can carry a large number of tasks by issuing a simple command, and the layered buffer will call the corresponding block to output the original instructions locally, which drives the signal converting circuit to generate the required underlying signals for chip control that minimize the communication overheads between the gateway and the processor-free local device. We implement a legal prototype and test it in 3 proof-of-concept application scenarios. Benefit by the chip's plug-and-play capacity, each scenario can be set up within few minutes. For instance, we can deploy a temperature sensor on the device to detect the ambient temperature, and now we can plug in a humidity sensor for new functions. The gateway can automatically detect the newly plugged chip. If we span the water, we can say the humidity increases and the temperature decreases accordingly. We first evaluate the response time after a chip is plugged in by using an oscilloscope to record the time duration from when the chip is plugged in to when the device is completely configured and available for use. We set the gateway CPU frequency at 1 GHz and change the communication data rate. The results show that all chips can be accessed within 130 milliseconds after they are plugged in. Then we change the gateway speed with fixed data rates and record the average time cost for responding to the aforementioned chips. The results show that even with slower CPU speed, the maximum time cost is less than 400 milliseconds, which is acceptable for chips plug and play. Next, we compare the power consumption of legal demo with common embedded devices. We used low-power Bluetooth for communication and sampled a 12-bit ADC. Benefit from processor-free lightweight architecture design, the legal demo achieves much lower overheads in computing aspects than that of a Arduino device. But the communication overhead is slightly higher because the legal device needs to receive control flow when the chip is first plugged in. We further evaluated the developer experience for system use. Since the unified chip description language is directly designed for functional chips, so it can greatly reduce time cost and code length for developing a chip description file. Besides, despite it is possible to support chips plug-and-play functionality in embedded platforms with wireless programming technology, the developer has to prepare all control programs and complete all debugs in advance to ensure the reliable interaction between the chip and onboard microprocessor, which takes much longer time than Lego do. In Lego, developers just need to write the description file with UCGL and a new chip can be supported. In this work, we propose a low-wall IoT application architecture called Lego, which supports chip-level reconfigurable end-device with cost-functional chips. The novel design contains a description language, a universal singular converting circuit, and a low-wall instruction orchestration model. This is the end of our talk. Thank you.